Imagine a neural network tasked with reading a handwritten digit. It looks at an image of a 2, but it spits out the wrong answer. It tells you it sees an 8. Correcting that mistake requires adjusting the network's internal parameters, the specific weights and biases determining how information flows from one layer to the next. In our model, we must navigate an array of over 13,000 individual dials. The standard approach finds the negative gradient of the cost function. But picturing a vector in a 13,000-dimensional space is beyond our imagination. We need a different way to interpret this data. Instead of an abstract vector, you can think of the gradient as a sensitivity map. Each component of that gradient corresponds directly to a specific weight or bias in the network. Understanding the gradient simply means figuring out exactly how sensitive the final cost is to a slight wiggle of each individual dial. This diagram isolates two specific weight parameters. If we calculate the gradient and the component for the first weight comes out to 3.2, while the component for the second weight is 0.1, we have our answer. That 3.2 value tells us the network's cost function is 32 times more sensitive to changes in that first weight than the second. Focusing on that first weight results in a more efficient reduction of the network's error. A tiny nudge there produces a significantly larger drop in cost than an identical nudge to the second. Requires calculating the specific proportional magnitude of every turn alongside its direction. Backpropagation is the recursive algorithm engineered to compute this exact sensitivity map for every parameter without relying on brute force calculation. To see how the algorithm works, we will ignore the dataset of tens of thousands of images and focus purely on how one single training example, our image of a 2, affects the network. Here are 10 output neurons in an untrained network. Their activations are random. We know their ideal state. The 2 needs a target of 1.0 and the rest 0.0. We cannot change output activations directly. We only influence the weights and biases feeding them. But we can define our goal. We want to nudge the number 2 neuron up and every other neuron down. The size of those nudges is proportional to how far away each current value is from its target. Backpropagation begins by defining exactly what the final layer wishes its state was, allowing us to reverse engineer those changes through the entire system. Let's zoom in on the number 2 output neuron and the specific layer of neurons immediately preceding it. An activation is defined as a weighted sum of the previous layer, plus a bias, all plugged into a function like a sigmoid or ReLU. To increase the activation of our target neuron, we have 3 levers. The first is to increase its specific bias. The second lever increases the weights of connections feeding into it. Notice the weights connecting to the brightest previous neurons have the highest leverage. Because they are multiplied by larger activations, increasing them strongly influences the final cost. This is reminiscent of Hebbian theory in neuroscience, the idea that neurons that fire together wire together. The algorithm mathematically prioritizes strengthening connections between neurons that are already active at the same time. The third lever is changing the actual activation levels of the preceding layer, making positive connections brighter and negative connections dimmer. Again, we cannot manipulate those previous activations directly. We only control weights and biases. Instead, we record a wish list of how the number 2 neuron desires those previous activations to change, sending those requests backward. But the other 9 output neurons are also sending their own requests backward to decrease their activations. The preceding layer sums these conflicting desires together, proportioned by the weight of each connection. This aggregate sum transforms the competing desires of the output layer into a single list of nudges for the second-to-last layer. Once we have this unified list of nudges, the problem looks exactly like the one we just solved at the output layer. We apply the same 3 levers process to this new layer. This creates a recursive loop. Calculate the desired nudges, adjust local weights and biases, and pass the changes backward. This process repeats sequentially, all the way back to the initial input layer, moving through the entire system layer by layer. This recursive cascade represents how a single training example defines its specific influence on the 13,000-dimensional sensitivity map. If we only adjust the network based on the 2 image, the network will simply learn to classify every image it sees as a 2. To find the true gradient, we must run this backward propagating cascade for every single image in the dataset. The algorithm records the desired weight and bias nudges for tens of thousands of examples and averages them together. This averaged collection of nudges is the true negative gradient of the cost function. However, executing this large-scale averaging for every single step of descent takes computers an unacceptably long time. Modern machine learning uses a shortcut, randomly shuffling the dataset and dividing it into mini-batches of, say, 100 examples. The backpropagation average is computed only for that tiny subset, and a descent step is taken based purely on that batch. This 3D topography shows the cost surface of the network. Because the batch step relies on incomplete data, the path, labeled here as SGD, is jagged and less direct than the true gradient. It is like a drunk man stumbling quickly down a hill, rather than a calculating man taking slow, perfectly measured steps in the exact downhill direction. Even with this stumbling path, rapidly iterating through mini-batches allows the network to reach a local minimum of the cost function in a fraction of the time. Backpropagation is the recursive, mechanical translation of errors into structural nudges. When paired with the speed of stochastic gradient descent, training models with thousands of layers and millions of parameters becomes mathematically feasible.